Okay, stoichiometry. This content can be the most difficult we will encounter in the course, but it doesn't have to be. It's a combination of mole conversions and balanced chemical equations. It can be conquered if you focus and pay close attention. If you daydream or give up easily, it will be more difficult than it actually is. So what is stoichiometry? Remember formula writing? Here are some formulas that we were writing before. That's part of stoichiometry, is knowing the proper formulas. Remember mole conversions, chapter 10. These should look a little familiar to you. Balancing equations. You should remember that. It's what we just finished. Well, stoichiometry is all that rolled into one. I'm going to give you an example of a stoichiometric problem. Butane, which is C4H10, completely combusts. If 35 grams of oxygen is used, what volume of carbon dioxide will be produced at STP? So there's a lot of information there. So the first thing we always need in stoichiometry is a complete, balanced equation. The reason we want that balanced is because that's going to help us to be able to convert from one to another species. So in this one, we have 35.0 grams of oxygen. It's in the second sentence. We want the volume of carbon dioxide, so that's liters of carbon dioxide. Now that's at STP. So we're going to be using the information we knew from chapter 10 and combine it with a balanced equation from chapter 11 to continue on to stoichiometry. So the way that this problem would work is you would start with what you have, your 35.0 grams of oxygen, and you convert it to moles because the coefficients in an equation are moles. So I use the molar mass of 32.0 grams of oxygen. I put 1 mole on the top, so my grams will cancel. Then I'm going to use my balanced equation. Carbon dioxide, there's 8 moles in the balanced equation, and oxygen, there's 13 moles. So that's my second part, is I'm going to convert from oxygen to carbon dioxide using the moles from the balanced equation. And I don't want moles of carbon dioxide, I want liters. So then I'm going to use my 22.4 liters per mole at STP. Then what I do is I do my math. I multiply and divide, and 35 grams of oxygen would produce 15.1 liters of carbon dioxide. Now, don't get crazy on me. This is just the beginning. I'm just showing you an example. We're going to do lots and lots of examples.
Amadeo, I'm headed out to get your mother, and I'll be back in a couple of hours. Now, don't touch these cookies. They're for her. I made her special lemon delight cookie recipe. I hope they're good. She's so picky.
I'm sure she'll love anything you make, dear.
I just want to impress her.
You will. Ciao.
Ciao.
These cookies taste like soap. A recipe is similar to a chemical equation. It tells you the exact amounts of each ingredient or reactants needed to create a product. Aha! Here is the problem. Using too much or too little of a reactant can spoil the product. She must have added too much baking soda. If you put too much baking soda in the cookies, The base reacts with the fat in the butter, and you get a product similar to soap. I'm going to have to bake another batch. But how am I going to know how much baking soda to use so that the cookies rise but don't taste like a soap? Let's see. Baking soda is important because it reacts with the citric acid in the lemon juice to create carbon dioxide and water. The carbon dioxide bubbles cause the cookies to rise. So, if we know how much citric acid is in our cookies, we will be able to calculate the mass of the baking soda. The recipe calls for 60 milliliters of lemon juice, and the concentration of citric acid in lemon juice is about 0.3 moles per liter, which means that we have to add 0.018 moles of citric acid. The stoichiometric relationship of citric acid and the baking soda is 1:1. So if we add 0.018 moles of citric acid, we have to add 0.018 moles of baking soda as well. Baking soda has a molar mass of 84.01 grams per mole. So to calculate the mass of baking soda, we multiply 84.01 grams per mole times 0.018 moles equals 1.5 grams. That's it! I need 1.5 grams of baking soda. I better start baking another batch. They'll be here soon. I'm famished. Oh, you made it, dear. Okay. Good to see you, Mother. Yes, we finally made it, and I am famished. Felicita told me she made a batch of my famous lemon delight cookies. Yes, and she worked really hard on them. I bet they're almost as good as yours. I'll be the judge of that. Oh, these are still warm. Felicita, these are wonderful.
Oh, I thank you. I'm so pleased that you like them. I was just following your recipe.
These are delightful, you've mastered. Looks like stoichiometry is pretty important for the chemistry of baking, too. Another great reason to never stop exploring your world. Non fermate ma esplorare vostro mondo. This should help my little boy.
Okay, at this point you will need your notes. So if you have not downloaded them, please do that before continuing. Okay, stoichiometry is the quantitative study of the relationships that exist in formulas and reactions. The word stoichiometry comes from the Greek stoichion, which means element, and metron, which means measure. So we're measuring elements. Chapter 10 showed the first aspect of stoichiometry, conversions among moles, particles, mass, and volume of formulas. This chapter explores the second aspect, relationships between reactants and products in a chemical reaction. Chemical reactions can be interpreted first and foremost as moles. The coefficients of a balanced chemical equation show the relative number of moles of reactants and products. So we're going to use the reaction of carbon monoxide and oxygen to form carbon dioxide. In this reaction, I have 2CO plus O2 yields 2CO2. So that means I have 2 moles of carbon monoxide, 1 mole of oxygen, and 2 moles of carbon dioxide. It can also be interpreted as representative particles, atoms, molecules forming the units. Now in this reaction, all of the reactants and products are molecules. So instead of saying 2 moles of carbon monoxide, I can say I have 2 molecules of carbon monoxide with 1 molecule of oxygen to form 2 molecules of carbon dioxide. It can also be represented as mass using molar mass. If I take 2 moles of carbon monoxide times its molar mass of 28.0 grams per mole, that's 56.0 grams of carbon monoxide. And then I take 1 mole of oxygen times 32.0 grams of oxygen, that's 32 grams of oxygen. If I add those up, I get 88 grams of carbon dioxide, which is 2 moles of carbon dioxide times 44.0 grams per mole. This verifies the law of conservation of mass, which we call LOCOM. In the law of conservation of mass, mass cannot be created or destroyed in any chemical process. The fact that the total mass of the reactants, 56 plus 32, equals the total mass of the products, 88, it will then obey the law of conservation of mass. This is the most important aspect of stoichiometry, because if we're doing stoichiometry labs, we don't have any instrument that's going to allow us to measure molecules or even moles, but we can easily measure mass using a balance. You can also interpret it as volume. It can be liters, but in this case, only at STP for gases only. So you can't get the volume of a liquid or the volume of a solid. But since all the reactants and products are gases in this, I can then take my 2 moles of carbon monoxide times 22.4 liters per mole, and I get 44.8 liters of carbon monoxide. And then to that, I add 1 mole of oxygen times 22.4 liters per mole, which is 22.4 liters of oxygen. And then I have 2 moles of carbon dioxide times 22.4 liters per mole, and I get 44.8 liters of carbon monoxide. Now notice, unlike the law of conservation of mass, there is no law of conservation of volume. Okay, we're going to start with a few problems, because the best way to do stoichiometry is to actually do problems. So here we have 2 moles of potassium chloride and 3 moles of oxygen are produced from the decomposition of 2 moles of potassium chlorate, which is KClO3. Write the balanced equation. So the first thing I'm going to do is I need to know the formula of potassium chloride and oxygen. So it says that I have 2 moles of potassium chloride, so there's my 2KCl, 3 moles of oxygen, 3O2, and they're produced, so they're on the right side of the arrow, from 2 moles of KClO3. Now that we have the balanced equation, we can actually do stoichiometry. So we can start with one thing and end with a different thing. So the second part is how many moles of oxygen are produced from 12 moles of potassium chlorate. So the first thing I'm going to do is set up my half times 1 over half problem. So I have from the problem 12 moles of KClO3. I want moles of oxygen. I have moles of KClO3, so that goes in the denominator. Then when I do my math, my units are going to cancel, and I will end with moles of O2. So now I'm going to actually place the numbers. From the equation, 12 moles KClO3. On the bottom, I put the coefficient from the balanced equation of 2 moles of KClO3 because the balanced equation allows us to go from one substance to the next. In from the balanced equation, I want moles of oxygen, so I'm going to use 3 moles from the balanced equation. This step is the most important step in stoichiometry, is switching from one to another species. So then I do the math. 12 times 3 divided by 2 gives me 18 moles of oxygen. Now notice I only have 2 significant digits in 12 moles, so I will have 2 significant digits in 18 moles. Using the equation from problem 1, how many moles of oxygen are produced from 14 moles of potassium chlorate. So I'm going to use the same equation. The only thing that changes in this one is instead of starting with 12 moles, I'm going to start with 14 moles. So I do the same thing. I have 14 moles of KClO3, so I put that first. I want moles of oxygen. I have moles of KClO3, so from the balanced equation, I'm going to put my 2 moles of KClO3 in the denominator, so my units cancel, and I'm going to put my 3 moles of oxygen in the numerator. So if you cancel your units, the only thing left is moles of oxygen, which is what we want. So 14 times 3 divided by 2 gives me 21 moles of oxygen. Once again, I started with 14, which is 2 significant digits, so I end with 21, which is 2 significant digits. Now, 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. How many molecules of water are produced from 2.0 times 10 to the 23rd molecules of oxygen? And then, how many moles of water are produced from 22.5 moles of oxygen? So the first thing, first and foremost, is I need my balanced equation. I have 2 moles of hydrogen, which is a molecule, and I have 1 mole of oxygen, which once again is a molecule. That's why they have the subscripted 2's. And I form 2 moles of H2O water. So the first problem is I want to go from molecules to molecules. So we just learned previous that you can go from molecules to molecules, from representative particle to representative particles, using the coefficients as particles. So I have 2.0 times 10 to the 23rd molecules of oxygen. Remember, we use U for molecules. I want to get rid of my molecules of oxygen, so I'm going to put 1 unit or 1 molecule of oxygen on the bottom to get rid of my UO2, and I put 2U H2O because molecules can be produced from other molecules. I do my math. 2 times 2.0 times 10 to the 23rd equals 4.0 times 10 to the 23rd molecules of water. And you would expect that because there's twice as much water as there is oxygen in the balanced equation. The second part, this time I want to go from moles to moles. So now I'm not going to look at the coefficients as molecules. I'm going to look at them once again as moles. So I'm going to start with my 22.5 moles of oxygen. I'm going to put 1 mole of oxygen on the bottom, so the units cancel, and 2 moles of water on the top. So the conversion factor is the same. It's just one is particles and the other is moles. So 22.5 times 2 is 45.0. Now notice in this one, I start with 3 significant digits, so I end with 3 significant digits. Make sure as we're going, you're not just copying them, but you're trying to do them as we go. Now, page 6, using mole ratios in stoichiometry. Mole ratios relate moles of unknown and known substances in a balanced chemical equation and are used to make stoichiometric mole-to-mole conversions between molar amounts of unknown and known substances. So what we have here is the combustion of propane. It's C3H8 plus 5O2 yields 3CO2 plus 4H2O. Now, if you look at the table, what it has is all the different reactants and products and the other things that are listed. So it's showing you all the possible combinations. So if I want to go from C3H8 to O2, I look up my equation. I have 5 moles of O2, 1 mole of C3H8. So our H times W over H is just shown for every possible combination in this table using the balanced equation. So, for each of the following problems, we're going to write the balanced chemical equation that represents the reaction. We're going to then complete the table below by identifying the known, the unknown, and the mole ratio that we want to use, using the table from the previous page as our template. So the first one is copper 2 oxide decomposes into copper and oxygen gas. Now I gave you the formulas, so all you really have to do is write the formulas and balance the equation. Do that at this time. Please pause. Okay, have you gotten your answer? It should balance as 2CuO yields 2Cu plus O2. Now I have added the forms, the states of each one in there because that makes it a complete equation. Try number 2. Ammonia, NH3, is produced by the reaction of nitrogen, N2, and hydrogen, H2. Write the balanced equation. Please pause. Okay, did you write it? Does your equation look like this? N2 plus 3H2 yields 2NH3. Number 3, the reaction of sodium and water produces sodium hydroxide and hydrogen gas. Write the balanced equation. Please pause. Okay, here's the correct balanced equation. To balance it properly, I need 2 NAs, 4 H's, and 2 O's on each side, and that balances by 2 Na plus 2 H2O yields 2 NaOH plus H2. When we were doing the previous chapter, I told you that you're going to need to be able to balance equations, and this is the beginning. You have to have a balanced equation before you can do any stoichiometry, because if this step is wrong, your mole ratio is going to be wrong, which then inevitably is going to make your final answer incorrect also. Number 4, the combustion of acetic acid produces carbon dioxide and water. So we want to do this. We have to think back. Combustion, that's when you add something to oxygen and you get carbon dioxide and water, but it says you're getting carbon dioxide and water, so I have to balance the equation by starting with the acetic acid, add to that oxygen to form carbon dioxide and water. Then I need to balance it. Please do that now. Here's the correct balanced equation. HC2H3O2 plus 2O2 yields 2CO2 plus 2H2O. On the left side, I have 4 H's, H plus H3. On the right side, I have 4 H's, 2 times H2. I have 2 carbons on the left, C2. I have 2 carbons on the right, 2C. I have 2 plus 4 is 6 oxygens on the left, and on the right, 2 times 2 is 4, plus 2 times 1 is 2, 6 on the right. The next one, 20 grams of iron 3 sulfide, Fe2S3, was prepared by heating iron and excess sulfur. So if I want to do that, I have to now look at this. I'm giving the product first because it says it was prepared by heating. So I'm going to balance my equation using Fe plus S yielding Fe2S. Please balance it. Okay, you should get this answer. 2Fe plus 3S gives me Fe2S3. 2 irons on each side, 3 sulfurs on each side. Now, you'll notice that I skipped the part on the actual stoichiometry. We're not quite ready to do those yet. So we will do those at a later time. But in order to do this, in the first one, you have copper 2 oxide. You want copper. So from the balanced equation, you're going to have 2 moles of copper over 2 moles of copper 2 oxide. So if you look back at the equation in problem number 1, you'll see that you had 2 Cu and you had 2 CuO. When you're doing a mole ratio, there should always be the same amount of the atoms that are on the top and bottom that are the same. So notice on the top we have 2 Cu, on the bottom we have 2 Cu. The second one, we have 22.0 grams of hydrogen. We want grams of ammonia. So I have 2 moles of ammonia from the balanced equation, 3 moles of hydrogen from the balanced equation. That's going to be our mole ratio. And if you check, 2 times 3 on the top is 6 H's. 3 times 2 on the bottom is 6 H's. The next one, we have 17.54 grams of sodium hydroxide. We want grams of hydrogen. So on the top, I'm going to put my 1 mole of hydrogen from the balanced equation. On the bottom, 2 moles of NaOH. But once again, you'll notice on the top, I have 1 times 2 is 2 moles, and on the bottom, I have 2 times 1 is 2 moles. Same thing for number 4 and 5. If you look at the mole ratios from the balanced equations, they will be the ones we will use. And as I said, we will complete the stoichiometry for these at the end of the chapter. We're going to use these as a review. At this point, you need not to do the stoichiometry. We're not ready for it yet.